Good evening, everyone. I hope I'm audible and my PPT is visible. It is already 5, but no one has joined till now. But since it is time, I will start with the live live discussion session. This is the course name is Soil Mechanics Geotechnical Engineering 1. This is the sixth week, and the topic of today's discussion is shear strength 1. This chapter, shear strength, has been divided into two parts as per the syllabus of this course. Soil Mechanics Geotechnical Engineering 1. In the first part, there will be some basic theoretical questions along with some basic numericals. And in the second part, that is the next week, upcoming week, Sunday, it is going to be purely numerical question answers. In today's discussion, as is the case with the usual classes, it will contain some MCQs, some true false statements, and some numericals. I believe there are 8 to 10 numericals today, and you're required to write down the questions first as I discuss them. I'll give you some time to solve them, and then after around 15-20 minutes, I'll be starting the class again. Then I'll be discussing the answers along with the concepts behind those solutions of all the questions. So it's already time, so I'm starting the class, the discussion session. I'll be dictating all the questions first, and then after a while I'll be discussing the solutions while explaining the concepts behind the solutions. So in this discussion, this has 20 questions combining of MCQs, false statements and numericals. And the first question is, the topic is shear strength. First question is, in the Mohr-Coulomb failure theory, the critical shear stress causing failure depends upon I repeat the question. In the Mohr-Coulomb failure theory, the critical shear stress causing failure depends upon, the options are properties of the material, normal stress on the failure plane, both of the above, none of these. I repeat the question once. In the Mohr-Coulomb failure theory, the critical shear stress causing failure depends upon, the options are properties of the material, normal stress on the failure plane, both of the above, or none of these. Next question. The unconfined compression test is generally applicable for. The unconfined compression test is generally applicable for. The options are dense sands, saturated clays, weathered geomaterials, or none of these. I repeat the question. The unconfined compression test is generally applicable for, the options are, dense sands, saturated clays, weathered geomaterials, or none of these. Next question. This is a very important numerical. A cylindrical specimen of saturated clay 4 centimeter in diameter and 8.66 centimeter length is tested in an unconfined compression tester. Estimate the unconfined compressive strength and shear strength of clay if the specimen fails at an axial load of 465 Newton and the change in length of the specimen on failure is 1 centimeter. The data in these questions are very important. Diameter, the length, the axial load, and the change in length. I'll repeat the question once. A cylindrical specimen of saturated clay 4 centimeter in diameter and 8.66 centimeter length is tested in an unconfined compression tester. Estimate the unconfined compressive strength and shear strength of clay. You have to find out both the unconfined compressive strength and shear strength of clay if the specimen fails at an axial load of 465 Newton and the change in length of the specimen on failure is 1 centimeter. The change in length is 1 centimeter, the actual load is 465 Newton, the original length is 8.66, diameter is 4 centimeter. You have to examine, you have to find out the unconfined compressive strength and the shear strength of clay. The material is subjected to unconfined compressive test. I hope it is clear. I'll go to the next question. Yes. A cylindrical soil specimen fails at an axial vertical stress of 160 kilopascal when it is laterally unconfined. The failure plane makes an angle of 50 degree with the horizontal. Now calculate the values of cohesion and angle of internal friction of the soil. I'll repeat the question once. A cylindrical soil specimen fails under an axial vertical stress of 160 kilopascal when it is laterally unconfined. The failure plane makes an angle of 50 degree with the horizontal. Calculate the values of cohesion and angle of internal friction of the soil. The data again here are very important. The vertical stress and the failure plane angle with the horizontal. Considering the horizontal to be the plane of major principal stress. Okay. Next question. The angle between the direction of the failure plane and the direction of the major principal plane is. What is the angle between the direction of the failure plane and the direction of the major principal plane? The options are, here phi is the angle of internal friction. The options are 90 plus phi, 90 minus phi, 45 plus phi by 2, or 45 degree minus phi by 2, where phi is the angle of internal friction or angle of shear resistance. Repeat the question. The angle between the direction of the failure plane and the direction of the major principal plane is, where phi is the angle of internal friction, 90 plus phi, 90 minus phi, 45 plus phi by 2, and 45 minus phi by 2. I hope it is clear. I'll go to the next question. The shear strength of a soil is a function of. The shear strength of a soil is a function of. The simple question. The options are cohesion only, angle of internal friction only, both of the above, or none of the above. I repeat, the shear strength of a soil is a function of cohesion only, angle of internal friction only, both of the above, or none of the above. Okay. Next question. The shear test most suitable in the field is. The shear test most suitable in the field is. The options are direct shear test, vane shear test, triaxial shear test, or unconfined compression test. Which tests among these tests are the most suitable for estimating shear strength of the soil in the field? You have to answer among these tests which test is the most suitable and the only suitable test for application in the field to find out the shear strength of a soil. And your options are direct shear test, vane shear test, triaxial shear test, or unconfined compression test. I hope it is clear. I'll go to the next question. Another numerical. A sensitive clay has a shear strength of 45 kilonewton per meter square in natural state and 15 kilonewton per meter square in remolded state. The sensitivity of the soil is. You have to find out the sensitivity of soil given that the shear strength in natural state and remolded state are given. The value of these are 45 kilonewton per meter square and 15 kilonewton per meter square. What will be the sensitivity of the soil? Your options are 30, 6, 1 by 3 or 3. I repeat the question. A sensitive clay has a shear strength of 45 kilonewton per meter square in natural state and 15 kilonewton per meter square in remolded state. The sensitivity of the soil is. The options are 30, 6, 1 by 3 or 3. I'll go to the next question. In a triaxial test, the relation between sigma 1, sigma 2 and sigma 3 is. Now I first need to explain what are the sigma 1, sigma 2 and sigma 3. In triaxial test, as we all know, that there is an axial stress and there is a confining pressure of, surrounding the soil sample. Now in this case, sigma 1, sigma 2 and sigma 3, what are these? So sigma 1, it is the major principal stress that is acting axially on top of the specimen, and that includes the confining stress also. So sigma 1, the pressure acting on the top axially on the sample. Sigma 2 is the intermediate stress and sigma 3 is the minor principal stress. So if we consider sigma 1 acting along the y-axis, then sigma 2 will be acting along the z-axis and sigma 3 will be acting along the x-axis. That means sigma 2 and sigma 3 will be acting along two mutually perpendicular horizontal axis, and sigma 1 will be acting on a mutually perpendicular vertical axis. So sigma 1 acting along the y-axis, sigma 2 acting along the z-axis, and sigma 3 acting along the x-axis. Now, as per this question which have been given over here, I am asking about the relationship between sigma 1, sigma 2 and sigma 3. Which among these relationships are correct with respect to sigma 1, sigma 2 and sigma 3 in a triaxial test? Among these relationships, which relationship is the correct one? Now, the options are sigma 1 equal to sigma 2 plus sigma 3, that is major equals to intermediate plus minor. Sigma 2 equals to sigma 1 minus sigma 3, that is intermediate equals to major minus minor. Option 3 is sigma 1 equal to sigma 2 equal to sigma 3, that is major equals to intermediate equals to minor principal stress. And option 4 is sigma 2 equals to sigma 3, that is intermediate principal stress is equals to the minor principal stress. So I repeat the question once. Triaxial test, the relationship between sigma 1, sigma 2 and sigma 3 is, I have explained this sigma 1, sigma 2, sigma 3 concepts. The options are sigma 1 equal to sigma 2 plus sigma 3, sigma 2 equals to sigma 1 minus sigma 3, sigma 1 equals to sigma 2 equals to sigma 3, or sigma 2 equals to sigma 3. Okay, I'll go to the next question. If the cohesion of a pure clay found in an unconfined compressive strength test is 1 kg per centimeter square, cohesion of a pure clay in unconfined compressive strength test 1 kg per cm square, the unconfined compressive strength in kg per cm square is, in this case, in an unconfined compressive strength test, the cohesion value is given, that is 1 kg per centimeter square. Using this cohesion value, you have to find out the unconfined compressive strength, the unconfined compressive strength in kg per centimeter square. The options are 0.5, 1, 2 and 4. If the cohesion of a pure clay found in an unconfined compressive strength test is 1 kg per centimeter square, the unconfined compressive strength in kg per centimeter square is 0.5, 1, 2 and 4. Next question. In an unconfined compression test, the soil fails under axial stress of 1.2 kg per centimeter square. The axial stress is 1.2 kg per centimeter square. The cohesion of the soil in kg per centimeter square is, in an unconfined compression test, the soil fails at an axial stress of 1.2 kg per centimeter square. The cohesion of the soil in kg per centimeter square is, the options are 0.5, 1.2, 0.6, 0.4. The axial stress is given, you have to find out the cohesion of the soil in the same units, kg per cm square. And then in the next question, calculate the angle of internal friction of the soil. In the previous question, there is this question, what is the angle of internal friction of this soil if the failure plane makes an angle of 65 degree with the horizontal. Considering the horizontal plane to be the plane of the major principal stress, the failure plane makes an angle of 65 degree. So what is the angle of internal friction? The options are 20, 10, 40 or 45. So in the first part, you have to find out the cohesion of the soil. Given that actual stress is 1.2 kg per cm square, and the second part, using the first and second data, or using the first or second data to find out the angle of internal friction of the soil when the failure plane makes an angle of 65 degree with the horizontal or the plane of the major principal stress. I hope it was clear. Next question. In a strain controlled shear box test, the shearing strain is, your options are decreased at a constant rate, increased at a constant rate, increased at a constant rate, option 3 increased randomly, option 4 kept constant. This is a part of the direct shear test, shear box test, where it has been asked to find out the behavior of the shearing strain, or the change, that the nature of change of shearing strain when the shear box test is strain controlled. I repeat the question again. In a strain controlled shear box test, the shearing strain is, options are decreased at a constant rate, increased at a constant rate, increased randomly, or kept constant. Okay, next question. Yes. In a direct shear test, the plane of shear failure is, in a direct shear test, the plane of shear failure is, the options are inclined at an angle 45 degree plus 5 by 2 to the major principal plane. Option 2 can be inclined at any angle. Option 3 horizontal. Option 3 is horizontal. Option 4 none of the above. Option 4 is none of the above. I repeat the question once. In direct shear test, the plane of shear failure is, the options are inclined at an angle 45 plus 5 by 2 to the major principal plane. Option 2 can be inclined at any angle. Option 3 horizontal, and option 4 is none of the above. This question is just in contrast to the failure plane of the triaxial test and to show the difference and the advantage of triaxial test over the direct shear test. So the plane of shear failure in this, the answer of the solution of this question is what we say, significant difference from the triaxial shear test. That's why this question is important. Okay, next question. This is a true false statement. This statement is true or false. We have to answer that. The statement is the Mohr envelope can be considered to be straight if the angle of internal friction is assumed to be constant. I repeat the question. The Mohr envelope can be considered to be straight if the angle of internal friction is assumed to be constant. So when we consider the friction angle of a soil to be constant at that time, can the Mohr envelope be considered to be straight or not? That is the question. You have to tell me whether this statement is true or false. I repeat the question once. The Mohr envelope can be considered to be straight if the angle of internal friction is assumed to be constant. Is this statement true or false? I'll go to the next question. Another true false statement. In direct shear test, there is an effect of lateral restraint on the soil sample. In direct shear test, there is an effect of lateral restraint on the soil sample. Is this statement true or false? The direct shear test is a basic test performed on soil sample for determining the shear strength parameters. All these questions is either an advantage or a limitation with respect to the direct shear test, and whichever is the limitation that has been overcome in the triaxial shear test, that we can cover in the next class, because the next class also you have to cover some parts of the shear strength. So today's questions are mainly from the direct shear test, and some questions are also from the triaxial shear test. I repeat the question. In direct shear test, there is an effect of lateral restraint on the soil sample. Is this statement true or false? And if it is true, then how is the lateral restraint acting on the soil sample? That also needs to be answered. If it is false, then if there is no lateral restraint, then how is the soil sample aligned in the shear box? And if there is lateral restraint, then how is the lateral restraint acting on the soil sample? Okay, next question. The complex stress conditions across the soil sample in direct shear test leads to the complex stress conditions across the soil sample in direct shear test leads to. Here it has been mentioned that direct shear test leads to complex stress conditions, and that is a well-known fact actually. But what does that condition, those complex stress conditions, what do those lead to? Your options are instantaneous mobilization of the entire soil strength. Option 2, progressive failure. Option 3, uncertainty in determination of strength parameters. And option 4, none of the above. In this question also, it needs to be answered. If one is correct, then what is the significance of the other two options? What is the meaning of the other two options? And whether or not they have a significant relation with respect to the direct shear test. This also needs to be answered. I repeat the question. The complex stress conditions across the soil sample in direct shear test leads to, the options are, instantaneous mobilization of the entire soil strength. Option 2, progressive failure. Option 3, uncertainty in determination of strength parameters. Or option 4, none of the above. Next question. This question is with respect to the vein shear test. A vein 10 cm long and 8 cm in diameter was pressed into soft clay at the bottom of a borehole. So the length is 10 cm and the diameter is 8 cm. Torque was applied, and when I say bottom of a borehole, it means the top and the bottom ends both are beneath the soil. Torque was applied and was gradually increased to 450 kg centimeter when failure took place. Subsequently, the vein was rotated rapidly so as to completely remold the soil. The remolded soil was sheared at a torque of 180 kg centimeter. Calculate the cohesion of the clay in natural and remolded states and the sensitivity. So, the dimensions of a vein is given and the torque applied was given to the original soil, which led to the failure. Then the vein was rotated to remold the soil, and the remolded soil was sheared at a torque of 180 in contrast to the 450 torque in the first case. Now we have to find out the cohesion of the clay in the natural and the remolded states. Cohesion in the natural and remolded states and the sensitivity. It has to be remembered that in clay the cohesion is the integral part of the shear strength, because clay is a cohesive soil. The angle of friction in place of clay is 0. I hope the question was clear. I go to the next question. The following results were obtained in a shear box test. Normal stress values are 1 and 2 in 2 samples, and the shear stress values are 1.3 and 1.85. There were one sample, not 2 samples, there were one sample, and the normal stress values were, in the first test was 1, in the second test was 2, and the corresponding shear stress was 1.3 and 1.85, everything in kg per centimeter square. Now you have to find out the cohesion and angle of internal friction. Only equations needs to be used, and diagram, there is no need of drawing any diagram in this case. Only equations needs to be formed and they need to be solved to find out the cohesion and angle of internal friction. More circle diagram is not required in this case. Normal stress 1 and 2, shear stress 1.3 and 1.85. Find out the cohesion and the angle of internal friction. Next question. This is the last question. Following results were obtained in a triaxial test. Total axial stress at failure is 18 kg per centimeter square. Cohesion is 3 kg per centimeter square. Angle of shearing resistance or angle of internal friction is 17.5 degree. Calculate the lateral pressure or the confining pressure. So when axial stress is given 18 kg per centimeter square, cohesion is given 3 kg per centimeter square, and the angle of friction or angle of shearing resistance is given 17.5 degree. Then what is the confining pressure or the lateral pressure applied in the test on a particular soil sample. The actual stress is 18, cohesion is 3, angle of shear resistance 17.5 degree. Okay, so these are all the questions. Now, if someone joins, they will be solving this. If anyone has joined in the middle, I don't know. But up till now, no one has joined. So I'll be joining back within another 15 minutes. If anyone joins, they can start writing the answers. After 15 minutes, I'll be starting the discussion, the solution, and the corresponding explanations of the answers will be given. Okay, so I'll be starting with the solutions of this questionnaire. I'll explain the solutions within the concepts behind them. So the first question was, in the Mohr-Coulomb failure theory, the critical shear stress causing failure depends upon. The correct answer is depends upon both the properties of the material and the normal stress on the failure plane. So yes, it depends upon both of the above, because when stress is applied, normal stress, and then a shear stress is applied in direct shear test or in triaxial test when shearing occurs, the properties of material also play a significant role. And this will be coming further as we see the equation of the shear strength, the main shear strength equation. There will be properties of the material involved along with the normal stress acting on the failure plane involved in the same equation. So we can say that the critical shear stress causing failure depends upon both the properties of the material and the normal stress on the failure plane. I hope it is clear. Next question. The unconfined compression test is generally applicable for. The unconfined compression test is generally applicable for. The correct answer is saturated clays. And why? Because in the equations acting with respect to this compression test, unconfined compression test. There are two parameters which are unknown, but there is a single equation which will be obtained at the end of the test. The parameters being C and phi. So we cannot solve one equations for two unknowns. Hence, we consider phi to be 0, and phi, that is the angle of internal friction, is 0 only in the case of saturated clays. So we can say that the unconfined compression test is generally applicable for saturated clays, only because here in the case of saturated clays the angle of internal friction is 0, and it can help us in solving because we get then one equation with only one unknown. I hope it is clear. Next question. Yes. A cylindrical specimen of saturated clay 4 cm in diameter and 8.66 cm length is tested in an unconfined compression tester. Estimate the unconfined compressive strength and shear strength of clay if the specimen fails at an axial load of 465 Newton and change in length specimen is 1 cm. So now we have to first find out the initial area. A1 is equals to pi by 4 d square, pi by 4 into 4 square, that will give us 12, almost approximately 12.56 centimeter square. Now on failure there will be a change in area, and that area will be equal to A2. A2 will be equal to A1 divided by 1 minus del L by L, and that area will be approximately equal to 14.21 centimeter square. 14.21 centimeter square. So if we have to find out the unconfined compressive strength, then the formula for that is QU, that is the unconfined compression test, that will be equals to the load at failure, axial load, that is 465, divided by 14.21, and that will give us a value first in Newton per centimeter square, and if we convert the value from Newton per centimeter square to kilopascal, then we have to convert the centimeter square to meter square, and then from Newton we have to convert it to kilonewton, that is we have to multiply the result with 1000, divide the result with 1000 and then multiply it with 10,000 to get a value of there. The approximate answer will be 327.23. That will be in kilopascal. That will be in kilopascal. Now Cu, that is the shear strength, as we all know, in saturated clay the shear strength is only a parameter concerning the cohesion because it has no friction angle. So the shear strength tau will be equals to the unconfined cohesion Cu, and that will be equals to Qu, that is the UCS, divided by 2, and that will give us a value of around 163.6. If we convert 327.23 divided by 2, 163 point approximately 62 kilopascal. Because the graph is like this. This is the circle, then this is the radius, this is the shear strength, this is Cu, and this entire thing is Qu. So the shear strength is half the value of the unconfined compressive strength. The shear strength will be half of the value of the unconfined compressive strength. The answer is 327.23 and 163.62. I hope it was clear. Go to the next question. A cylindrical soil specimen fails under an axial vertical stress of 160 kilopascal when it is laterally unconfined. The failure plane makes an angle of 50 degrees with the horizontal. Calculate the values of cohesion and angle of internal friction of the soil. In this case, the axial stress is given, it is sigma 1, it is equals to 160 kilopascal. 160 kilopascal. Alpha, the value of alpha is 50 degree. Now, first of all, we can find the value of cohesion and internal friction, but first of all, we need to find the value of internal friction. We can do it either ways. So, if alpha is 50 degree and the formula for alpha is 45 plus 5 by 2, then on rearranging, we can say that phi is equal to 50 minus 45, 5 into 10, 10 degree. 10 degree. Phi is equals to 10 degree. If phi equals to 10 degree, then we have an equation is sigma 1 equals to sigma 3 tan square alpha plus 2c tan alpha. Sigma 3 tan square alpha plus 2c tan alpha. This is laterally unconfined. You can see it is laterally unconfined. Hence, the sigma 3 value will be equal to 0. The sigma 3 value is 0. Hence, the value of c will be equals to sigma 1 divided by 2 tan alpha. Sigma 1 divided by 2 tan alpha. And that will give us a value of 67.12 kilopascal. 67.12 kilopascal. Sigma 1 value is given, alpha is given. We can find out with the help of alpha, we can find out the angle of internal friction, which is 10 degree, and with the equation sigma 1 equals to sigma 3 tan square alpha plus 2c tan alpha, we can find out the value of c, that is sigma 1 divided by 2 tan alpha, that is 67.12 kilopascal. I hope it is clear. Go to the next question. The angle between the direction of the failure plane and the direction of the failure plane, and this is the plane of the major principal stress. This is the major principal stress sigma 1, and this is the failure plane. The angle in the plane is alpha, and as per the previous question also, alpha equals to 45 plus pi by 2. This plane makes an angle of 45 degree plus pi by 2, where phi is the angle of friction or friction angle. Phi is the friction angle. So the failure plane makes an angle of 45 plus pi by 2 with the direction of the major principal plane. I hope it is clear. I go to the next question. The shear strength of a soil is a function of. The shear strength of a soil is a function of. The options are cohesion, angle of internal friction, both of the above, none of the above. So the shear strength equation is tau equals to C plus sigma tan phi. Tau equals to C plus sigma tan phi. Tau equals to C plus sigma tan phi. So here the shear strength tau is a function of cohesion and also the angle of internal friction. And as for the first question, the shear strength also depends on the properties of the material, that is C and phi, and also on the normal stress on the failure plane. So in this case it is proved, that is C and phi, C, phi and sigma all form as variables to the function, that is the shear in the soil. So both of the above, the cohesion and the angle of internal friction, both are important parameters for determining the shear strength of the soil. Next question. The shear test most suitable in the field is. Direct shear test and triaxial shear tests are performed in the laboratory. Unconfined compression test is a type of triaxial test where there is no confining pressure. So all the tests, direct, triaxial and unconfined, are performed in the laboratory except the vane shear test. We have a vane that rotates in the soil sample. We have a numerical with respect to that later, and an equation has been formed with respect to the torque of the rotating vane and the shear strength of the soil. In that way, in the field, in situ conditions, we can find out the shear strength of the soil using the vane shear test. Using the vane shear test. I hope it was clear. Okay. I'll go to the next question now. A sensitive clay has a shear strength of 45 kilonewton per meter square in natural state and 15 kilonewton per meter square in demolded state. The sensitivity of the soil is. The sensitivity of the soil is. A sensitive clay has a shear strength of 45 kilonewton per meter square in natural state and 15 kilonewton per meter square in demolded state. So in this case, sensitivity, the formula is the unconfined compressive stress Cu undisturbed, that is in natural state, the actual formula, divided by Cu, that is the compressive strength remolded. But as we know that compressive strength is equals to, or we can write like this, yes, we can write the shear strength in the case of clay, it has no friction, that is equals to C in unconfined state, and C is equals to Cu by shear strength, the ratio of this shear strength can also form the equation for sensitivity. So we can write like this: sensitivity equals to Cu undisturbed, Cu natural, and then divided by Cu remolded. Now Cu undisturbed in the natural state is 45, Cu remolded is 15, 45 by 15 gives us 3. So the value of sensitivity of the soil is 45 by 15, that is 3. So here is the equation, that is shear strength or compressive strength or undrained cohesion in the natural state divided by the same parameter in the remolded state. We can find out the sensitivity. Here the shear strength in natural state is 45 and in the remolded state is 15. Hence we can divide both of them and we can get 3, that is the sensitivity of the soil. I hope it was clear. I'll go to the next question now. In a triaxial test, the relation between sigma 1, sigma 2 and sigma 3 is. Apparently this was a tricky question because sigma 1 does not come in this relationship. The actual answer is option number 4, sigma 2 equal to sigma 3. If sigma 1 is this acting in the vertical direction in the y-axis, sigma 1, and sigma 2 and sigma 3 is this acting in the z direction, this is sigma 2, sigma 2, and this is sigma 3. Then we can say it is the fact that in triaxial test the confining pressure acts all around surrounding the soil sample and normal stress is being applied from the top. So everywhere around the soil sample the pressure is uniform, the pressure is equal. Hence the pressure acting on the z direction and on the x direction is same, that is sigma 2 equal to sigma 3. That is sigma 2 is equals to sigma 3. That is the intermediate principal stress is equal to the minor principal stress. Intermediate principal stress is equal to the minor principal stress. I hope it is clear. This is the state of stress sigma 1, sigma 2 and sigma 3, where sigma 2 equal to sigma 3, and then we can find out the diabatic stress as per the given relationship in the triaxial testing system. I hope it was clear. Go to the next question. Yes, another numerical. If the cohesion of a pure clay found in an unconfined compressive strength test is 1 kg per centimeter square, so cohesion unconfined, it is undrained cohesion found in an unconfined compressive strength test is 1 kg per centimeter square. 1 kg per centimeter square. The unconfined compressive strength, that is QU, as I have mentioned previously, this is the graph. This is the normal stress versus the shear stress. This is the Mohr circle, and in this case this is the value of compression. Here sigma 3 is equal to 0 because it is unconfined, hence it is starting at the origin, and the diameter of this circle is 2u, that is the unconfined compressive strength, and this is the radius. The maximum value is the shear strength, that is tau, that is equals to Cu. So Cu is the radius and Qu is the diameter. So we can say that Cu equals to Qu diameter divided by 2, or the unconfined compressive strength Qu equals to twice of the radius, that is twice of Cu. So the unconfined compressive strength in the unconfined compressive strength test is twice the value of the shear strength or the value of the undrained cohesion, because the undrained cohesion is nothing but the shear strength of the soil. So in this case, twice of Cu means twice of 1, that is the value is 2 kg per centimeter square. So the answer of this question compressive strength, value of the unconfined compressive strength of this soil sample is 2 kg per centimeter square. Value of the unconfined compressive strength is 2 kg per centimeter square. I hope it is clear. I'll go to the next question. In an unconfined compression test, the soil fails under an axial stress of 1.2 kg per centimeter square. The cohesion of the soil is. Now, since the axial stress is given, the sigma 1 equals to 1.2 kg per centimeter square, and it is, as I said, it is an unconfined compression test. That means it is performed in saturated place at phi equal to 0. Then we can say that the axial stress at which the soil fails, that is equal to the unconfined compressive strength of the soil, that is equals to 1.2 kg per centimeter square. Then what is the value of the cohesion of the soil? So as I have said previously, I will draw the diagram once again over here. This is the value of the Mohr circle for sigma 3. This is the value of the Mohr circle for sigma 3 equal to 0. This is sigma 1. This is the value of the unconfined compressive strength, that is QU, and this is the value of the maximum shear strength, that is CU. Cohesion is equal to the shear strength. So in this case, QU equals to, again, QU divided by 2. QU divided by 2. That will give us what? That will give us 1.2 divided by 2, that is 0.6. 0.6 is equal to 0.6 kg per centimeter square. So this is 0.6 kg per centimeter square is the answer of this question. Again, in the next question, it has been said, if angle of internal friction would have come into play, that is, if the soil was totally not saturated clay, if it has any friction angle associated with it, then what will be the value? Actually, this question is totally unrelated, but it has been made to seem that it is related, just to confuse the readers. But this question is totally separate. This question can be interpreted like this: if you can remove this part in the previous question, then what is the value of the internal friction angle when the failure plane makes an angle of 65 degree with the horizontal? So the alpha value, that is the angle of failure plane with the horizontal, is 65 degree. 65 degree alpha, and the formula for alpha is 45 plus phi by 2. 45 plus phi by 2. Now if we rearrange this equation again, we can find out the value of phi, that is the angle of internal friction, that is 65 minus 45, 20 into 240, will be equals to 40 degree. The angle is 40 degree. So the angle of internal friction is 40 degree when the failure plane makes an angle of 65 degree with the horizontal. I hope it is clear. I will go to the next question. Yes. In In a strain controlled shear box, the shearing strain is, first of all, if in a shear box test there is a normal load like this, this is a soil sample, normal load, and then there is a shearing load, keeping the base plate as fixed in the shearing load. If the shearing load is kept constant, then there will be a certain chance of the soil failing in shear. If the shearing load is decreased at constant rate, then the soil sample may not shear at all, may not fail at all. And if it is increased randomly, then it will be difficult to keep a track of the strain and the stress values, strain and the corresponding stress values. Hence, in order to cause the sample to fail, what we can do is, what we do actually is, in direct shear test, in the shear box test, in a strain controlled shear box test, we increase the shear strain at a constant rate. The shear strain, that is epsilon, if we consider, we increase the shear strain at a constant rate, and we measure the shear strain in a probing ring and the corresponding shear stress in the dial gauge, and it is increased for making the soil fail, and it is at a constant rate so as to note down the value, so that it will help us in plotting the Mohr circle at the end. So, in a strain controlled shear box test, the shearing strain is increased at a constant rate for causing shear failure in the soil sample under consideration. So, the second option is the correct one. The shearing strain is increased at a constant rate. I hope it is clear. Yeah. Okay. Next question. Okay. In a direct shear test, the plane of shear failure is. In a direct shear test, the plane of shear failure is. Now, as I have shown in the previous diagram, I will also show it over here once more. If this is the soil sample in a shear box, and the normal stress is applied over here like this, and this is the direction of the shear stress. This is tau applied over here, this is sigma applied over here, and this is completely horizontal. The soil will essentially fail in a plane which is parallel to the direction of the applied shear stress or the shear force. Then we can say that the failure plane will be essentially horizontal. The failure plane is actually predetermined in the case of a direct shear test, which is unlike the condition in the triaxial shear test. In triaxial shear test, the failure plane is inclined at an angle of 45 plus pi by 2. In triaxial shear test, the failure plane is inclined at an angle of 45 plus pi by 2. This happens in triaxial. That is more closely matching to the field conditions. It cannot be inclined at any random angle, first of all, and in the direct shear test, the failure plane is essentially horizontal, and the most important thing is it is predetermined. It is predetermined. Predetermined because we assume the failure plane to be horizontal, and then we perform the test. So, in the case of direct shear test, the failure plane is horizontal and predetermined. I hope it is clear. I'll go to the next question. The Mohr envelope can be considered to be straight if the angle of internal friction is assumed to be constant. So, this is sigma and this is tau. If this is a straight line with respect to sigma and tau, and this is the angle of friction, we consider cohesion to be 0, so there is no intercept. This is the angle of friction. Then for a perfectly straight line, this will be constant. This will be constant. So, essentially, if the angle of internal friction is assumed to be constant, then it will give us a straight line in the Mohr envelope. 3 is simple, so the answer is true because mode envelope is a straight line when phi is constant. But what is the otherwise case? If phi is not constant, if the mode envelope we get is like this, a curved line, then the mode envelope it will vary as per the tangent. So in this point it will be the tangent to this point, and this point it will be the tangent to this point, and hence we will get different values of phi because phi is different. This is phi 1, this is phi 2. So phi is different, and hence the mode envelope is different. Considering the tangent to be different, if the mode envelope is a curved one, uh, the mode envelope will be a curved one, and the value of phi will be different as per the tangent of the curve. So I'll just draw it in a clear way. Explain it once again. I guess I had fumbled a few times. Yes, so this is the curved plane and this is the mode envelope. This is the envelope. Then the angle of internal friction phi will vary as per the tangent to this envelope. At this point, this is a tangent. At this point, this is the tangent. So at each and every point, the value of the friction angle will vary as per the tangent to the failure envelope. I hope it is clear. Okay, I'll go to the next question. In a direct shear test, there is an effect of lateral restraint of the soil sample. Yes, lateral restraint of the soil sample, it is true. Why? There is a lateral restraint because if we see from the top, this is the soil sample, it is kept in a shear box which is being surrounded on all sides. So when this is the area, this is the normal force, it is not looking like that, but I will just draw it in a cross section wise. This is the cross section, and the front part is the wall of the shear box wall. So if we apply the load, the force, that is the shear force, inducing a shear stress on this sample, then it will shear while it is in contact with the wall. So there will be a lateral restraint due to the side walls of the shear box, and this is one of the drawbacks because in the field conditions lateral restraint rarely exists. Because of these drawbacks, it is better to perform triangle test rather than the direct shear test. I hope it is clear. I'll go to the next question. The complex test conditions across the soil sample in direct shear test leads to, because the stress conditions are complex, the soil sample does not fail at once. It takes time to fail as per the incremental values of shear stress induced at the soil sample due to the applied shear force. So the first option is wrong because instantaneous mobilization of the entire soil strength means the soil sample fails all at once. It doesn't happen. Option 3 is uncertainty in determination of stress parameters. There is no uncertainty because we can get the value of normal stress, we can get the value of normal stress, we can get the value of shear stress, we can plot a graph, that is normal stress and shear stress, sigma and tau, we can plot a graph, and then we can find out the value of the movement envelope and the value of C and phi. So there is no uncertainty in determination of the strength parameters. But what happens is, because of the complex test conditions, there is a progressive failure. The soil sample fails gradually and the intensity of failure increases with respect to time. Because of which the soil strength is not mobilized at once, and it does not lead to instantaneous failure, it leads to progressive failure of the soil sample. And hence, this complex test conditions makes it difficult to identify the failure mechanism conditions in the direct shear test leads to progressive failure of the soil sample, in which the entire soil strength is not mobilized simultaneously. So both these options are actually wrong. It is actually false. Only this statement is correct. Progressive failure. I hope it's clear. I'll go to the next question. Yes, vein shear test. So the dimensions of the vein is given 10 cm long, 8 cm in diameter, pressed into soft clay. So we can consider that the top and the bottom of the vein was completely inside the soil sample, into the soil in the field, and we can use a formula that is torque equals to pi d square tau f h by 2 plus d by 6, h by 2 plus d by 6. Now, in the first case, when the natural state was present in the soil, the torque was 450 kg centimeter. The torque was 450 kg centimeter, and we also know that it is soft clay. It is soft clay, so soft clay will have zero angle of internal friction, and hence tau f, that is the shear strength at failure, will be equals to the value of Cu, that is the undrained cohesion. This is the cohesion which is being asked. So putting cohesion in this equation, and in the first case if we put T equals to 450, T, capital T equals to 450, the H, that the length or the height of the vein is 10, and D diameter is 8, we can rearrange this equation, obtain the value of Cu natural to be equals to 0.35 kg per centimeter square. Now in the remolded soil, what happens is the torque applied for failure was 180 kg centimeter. The torque applied for failure was 180 kg centimeter. So in the next equation, what we have to do is replace 450 by 180 in place of capital T, and all the parameters remaining same, that is h equals to 10, d equals to 8, and we get Cu remolded to be equals to 0.14 kg per centimeter square. That is, there is a loss in cohesion due to remolding of the soil. There is a loss in cohesion due to remolding of the soil. So these are the first two answers. That is cohesion of clay in the natural and the remolded states, natural state and remolded state. Now the sensitivity, value of sensitivity is cohesion in the natural state by cohesion in the remolded state, or shear strength in the natural state, or shear strength by shear strength in the remolded state, whatever. This is just the ratio of the natural condition to the remolded condition. That is 0.35 divided by 1.4. 0.35 divided by 1.4. No, 1.4 is 0.14. 0.14, and we get the value of 2.5. 2.5. This is the value of sensitivity of this soft clay sample. Sensitivity of this soft clay sample when the following conditions exist, or the following conditions appear after a vein shear test in the field. So this is the only formula that comes into play. I hope it was clear. I'll go to the next question. I'll go to the next question. following results were obtained in a shear box test. The normal stress values are 1 and 2, and the corresponding shear stress values are 1.3 and 1.85. 1.3 and 1.85. Now we have to find out the cohesion and the angle of internal friction. So as we know, the basic equation of shear strength is tau equals to C plus sigma tan phi. So we get two equations and we'll have two unknowns. That is, the first equation will be shear stress is 1.3. That is 1.3 equals to C plus normal stress is 1 tan phi. That is equation 1, and then we'll get 1.85 equals to C plus 1, not 1, in this case it is 2, normal stress is 2 tan phi. This is equation 2. Now two equations, two unknowns, we can solve this simultaneously. We can subtract 1 from 2. We can do, that is equation number 2 minus equation number 1 will give us tan phi. Tan phi equals to 0.55, which will give us phi equals to almost 28.81 degree. 28.81 degree. So we have found out the angle of internal friction. Now putting the value of tan phi equal to 0.55 in the equation 1, we get the value of C. What is the value of C? We'll be getting, that is 1.3 minus 0.55. We get the value of 0.75. That is C equal to 0.75 kg per centimeter square. So the value of phi, or the angle of internal friction, is 28.81 degree, and the value of C, or cohesion of the soil, is 0.75 kg per centimeter square. I hope it was clear. I'll go to the last question. The following results were obtained in a triaxial test. Total axial stress at failure. Okay. So sigma 1 in the case of triaxial test, sigma 1 equals to 18 kg per cm square. Cohesion C equals to 3 kg per cm square. Now we have phi, angle of shearing resistance, or the angle of internal friction, is 17.5 degree. From this phi we can find out alpha. What is the value of alpha? Alpha equals to 45 plus phi by 2. That will give us a value of 17.5 divided by 2 plus 45. It gives a value of 53.75. It gives a value of 53.75 degree. Now we have this equation, sigma 1 for triaxial test condition equal to sigma 3, is the confining pressure, sigma 3 tan square alpha plus 2c tan alpha, where alpha is the angle made by the failure plane with the plane of the major principal stress. So we have to find out sigma 3 over here. So we can rearrange this equation and write it like this: sigma 3 equals to sigma 1 minus 2c tan alpha divided by tan square alpha. Sigma 1 minus 2c tan alpha divided by tan square alpha. We get a value of around 5.276 kg per centimeter square. I'll just take it once again. C tan alpha into 3 into 2. Sigma 1 is 80 divided by tan alpha is 5.276 or 5.28. We're getting a value of around 5.28 or 5.276 kg per centimeter square. Okay, so I hope the session was clear, the session was useful for everyone. We'll meet next Sunday with the second part of the shear strength, and that will include more number of numericals and more concepts on the triaxial tests, and also if some problems of pore pressure, I'll be trying to incorporate some problems of pore pressure in the next session. So thank you.